Thank you for inviting me back this time. I was disappointed I couldn't get to come to Morocco, having been there for ICMCS 18. I was looking forward to coming back, but hopefully in the future. All right, so Steiner Minimal Trees. I want to give you an introduction to them, talk about some of the parallel computation, where we're going in the future, and we'll try to fit that all in the 30, 35, whatever minutes time window we can do it in today. I do want to say good morning. I guess it's afternoon where most of you are. I'm, I believe, 8-hour difference time-wise from Morocco. So I had to make sure I had the times lined up to make sure I was here at the right time. I'm sorry I wasn't here earlier to hear the full talk by Professor Jonas, but I was enjoying hearing the ending of it. First off, let's talk about where I am, because some of you have probably never been here. The United States is let's get my pointer to a laser so I can show you things. Nevada is in the western half of the United States. And most of you, when you hear Nevada, you think of Las Vegas. But I'm not in Las Vegas, I'm up in Reno. And that's about round trip distance I was trying to estimate from Rabat to Marrakesh and back for the full drive. So that's an interesting distance. We're actually farther west than Los Angeles, if you want to think of it that way too. Reno is a beautiful city. It's not moving forward because we're sitting at about 4,500 feet, so about 1,500 meters in elevation. Have mountains, have full 4 seasons, so it's a really gorgeous town to be in. In the fall, we typically have balloon races, which are really fun to be part of. I've gotten to go up in a couple of them, so that's a really fun thing to do. But the thing I enjoy the most is going up over this mountain here and skiing up there during the winter. So hopefully we'll get some snow for that. That's my son and daughter and wife down there, so we were having fun up on the hill. Our campus is on the north end of town. We are currently at about 22,000 students. It has grown in the time I've been here. We do have full winter with some older buildings, but we have some nice part during the spring. This is where graduation will take place in May, we hope. We are out on the quad for everybody to be finishing their bachelor's, their master's, and PhD students to graduate. The campus has been growing. As I said, we've had a lot of new buildings. And I've had to move into a brand new building this past semester. So that's been the rough part, is moving. But we have some nice new space for the College of Engineering, which has been really helpful. All right, so Steiner Minimal Trees. Let's go to the problem statement. Given a set of n cities, we want to construct a network. Think of this as a communication network, a road network, whatever you want to do, but we want to have it of minimum length. The problem is pretty simple, but the catch is that you're allowed to add junctions. So if you're thinking of a computer network, we're allowed to add a junction at that network, but the problem is, how many junctions do we want to add? And we have to place them to minimize the amount of length of the entire network, because we've got to have that as the shortest cost possible thing. So we're trying to optimize length. So let's go to the easy part. We're going to start with 3 points. Point A here, point B up here, and point C here. And we're going to take 2 points, in this case, A and C in our example. And we're going to figure out how we construct this minimal network. We could just draw the lines from A to B to C and have a nice short spanning tree. That's the typical thing you learn in your basic data structures class as you're programming algorithms for that. You build a spanning tree. But we're going to come up with a network that's actually shorter. So the first step from a geometry point of view is to construct an equilateral triangle. In this case, we're going to do A and C, and we're going to form this equilateral triangle with X. Then we circumscribe that triangle with a circle. And if B is inside the circle, we're done. We don't do anything else. We just do the ABC. If B is outside, which it is in this case, we're going to draw the line from X to B, and we're going to create a junction at this point P where that line crosses the circle. And that is actually where we put what's called the Steiner point. And so we then have the network from A to P P to B, and P to C. So we end up with Steiner point, and that is actually a shorter network than the spanning tree that we started with. Now, as typical in a lot of mathematical fields, a lot of people studied this problem. We had independent solutions. Fermat, Torricelli, and Cavalieri all developed independent solutions for this problem. And then we come to the 19th century. University of Berlin, Jacob Steiner, he said, let's make this a little bit bigger of a problem. Let's go from 3 points, but let's go to as many as you want. And he said, well, let's keep it with adding 1 point. And he generalized this problem for arbitrary large number of things, but you could only add 1 junction. And that basically creates, from the physics point of view, or from the graphics side of it, what you want to call the center of mass. And this is how we deal with bodies in graphics, where the center of mass when we're doing collisions and 3D visualizations of it. In 1934, Jarnik and Kossler said, wait, why are we only adding 1 point? Let's add as many as you want. So they decided that you could add as many as you want, and your whole goal was to minimize the network length. And then we had this interesting thing, because Jarnik and Kossler proposed the problem, but in 1941, Courant and Robbins had a book. It's a very good book that I would recommend. The title of it is called What is Mathematics? It was published by Oxford University Press. I believe there's a second edition out. And they linked that problem that was proposed by Jarnik and Kossler with the name Steiner. And they named the problem the Steiner Minimal Tree Problem. And that name has stuck since 1941. Now, if you want to go back and read some stuff, I always like to give some background literature for people. Byrne and Graham had a really good article in 1989 in Scientific American called The Shortest Network Problem. And that's an easy one to find online. There's also an excellent survey paper by Huang and Richards in 1992, where they talked about Steiner tree problems, not just the Steiner minimal tree, but all these other problems that could happen on it. And then there was a book published in 1992 also by Huang, Richards, and Pawel Winter called The Steiner Tree Problem. I have a copy of that one on my shelf in my office at school. And it talks about all sorts of different parts of this problem and covers the literature and the breakdown of it. It's a really nice book, but not cheap, I'm sorry. So the basic things that we want to know at this point. All those original points that we started with will either have degree 1, 2, or 3. So in this case, we're going to have 1 edge coming out, or 2 edges, or possibly 3 edges, but that's the max out of any vertex that's in the original thing. The Steiner points that we add will all have degree 3. They will all have 3 edges. So if we go back to that problem a while back, where we saw this one, this point P, the Steiner point, it has degree 3 because it has the BP, the AP, and the CP edges. So those are all going to be degree 3. And then any 2 edges meet have to have an angle of at least 120 degrees. So therefore we can have a max of degree 3. And the construction for the 120 degrees is a geometric construction, because if it was less than 120, we could have had another Steiner point that was probably added to the whole network. But I'm not going to spend too much time on the geometry pieces here. So we had that problem, the Jarnik and Kossler problem. They proposed it, and for the next 30 years, we had a bunch of heuristics. And typically the heuristics were based on the minimum spanning tree. We talked about that and tried to figure out how to use the minimum spanning tree to figure out what we could do. 1968, for example, Gilbert and Polyak linked the length of the Steiner minimal tree to the minimum spanning tree. And they said that the Steiner minimal tree can never be shorter than the square root of 3 over 2 times the minimum spanning tree. Or if we want to write it a little better, we can say the length of the SMT is greater than or equal to the, I'm going to put 0.866 as an approximation for square root of 3 over 2 times the minimum spanning tree. So we have an upper bound and a lower bound. And that's really a nice place to work with when we're working on some algorithms and calculating pieces. Then we shift to 1961, and Melzack extended the 3-point figure. And this is a major piece in the computation for Steiner minimal trees. And he said, basically, we can do it recursively. And if you think back to recursion, when you're taught about recursion and coding, can we take a big problem and break it into one or more smaller problems and then solve those smaller problems? And so that's what he's doing recursively. So we can reduce the n-point problem into a set of n-1 point problems. So let's think back to this 3-point problem. We have our AC, and we have 2 possible points. We put the x down here for our equilateral triangle. We could have put the x way up here for the equilateral triangle as well, right? So they say, take those 2 options, x1 and x2, and create 2 smaller problems. Replace A and C with x1 in one of them, and replace A and C with x2 in the other one. And now we have 2 problems of a smaller size. And therefore we can go through and calculate what the Steiner minimal tree length is going to be. And they went through and showed that they could do that. And it was basically continuing from there on down to make the problems smaller until we got to a place where we had 2 vertices with an edge between them, and we're done. But that's a recursive solution, and that grows exponentially, which can make things really nasty as far as how long it will take. And we ended up with a recurrence relation. And from a theoretical point of view, we see the exponential piece here. And Gary, Graham, and Johnson in their works have shown that the Steiner minimal tree problem is NP hard. And they said, well, we can actually make it NP complete if we round the distances to discrete values. So instead of having floating point distances, we're going to have integer distances. So if we round it to discrete values, it is an NP complete problem. And that means there will be no polynomial nice algorithm that's going to be there. So it's going to be growing up rapidly. So 1967, Ernie Kane, interesting guy to meet. Ernie Kane clarified some of the proof of Melzack and then used it to develop some code. He was a good mathematician, computing background, and he worked with somebody else at his university, and they could compute Steiner minimal trees for placement of any 7 vertices. You put the 7 vertices out there and they could run the code on it. And they were so excited because that was the first time it had ever been done for anything bigger than 3. So they were able to expand it quite rapidly in 1967. At that point, I was working on my PhD back in the 90s, and I started looking at this problem, was doing a simulated annealing approach. This is an approximation algorithm. I wanted to see, could I do some approximation on this part? And we put together a simulated annealing where we said, we know what the exact solution is for some of these problems. We know what the spanning tree is. Let's figure out how far we can move from the spanning tree to the exact solution, because simulated annealing is an approximation. So we're going to have an error. So what is our coverage, or the better part of the non-error? And we were able to come up with simulated annealing values that fit here for the 6 problems I have shown here. And basically we're between 96 and almost 99%. So we were able to have a simulated annealing approach that gave us really good, fast approximations. And so that was the next step that we went through. This was probably the springboard for one of my first publications in this field. And it helped me realize that this was an area I really enjoyed working on for my PhD. So I spent the next bit of time doing more work in this direction, working on graph algorithms. So let's talk about this problem. We already showed a recursive solution to it, but we want to talk about the next stuff that came after that. 1968, Gilbert and Polyak, they said the SMT, the Steiner minimal tree for a set of points S, must lie within the convex hull of S. So basically, if we have these points here on the plane, the convex hull is this hull which has everything inside of it. And this is an important piece for graphics because we use the convex hull when we're dealing with object collisions. So if you think of things that are moving in graphics, when they hit each other, they use a hull to be able to do that collision detection. So Shamos, in his PhD dissertation, proposed a divide and conquer for the convex hull. And that's the basis for parallelizing the convex hull in almost any piece of code. And I'm not going to go through the algorithm, but I'm going to mention it here just so people that may want to go back and read can go look for some stuff. Basically, that's the piece that got us moving in the right direction. Now, as we look at these problem decompositions, we end up with this thing where we say, if property P exists, then the problem can be split into subproblems. And this is really important when you want to talk about something that's really hard to solve, whether it's a complex, whether we're talking about Steiner minimal trees, or as Gary and Johnson talked about it, NP complete problems. If we can split them into subproblems, it makes it much, much more solvable. And this is important for non-polynomial algorithms. And when we talk about the SMT, Steiner minimal tree, it's usually a geometric issue. So you've got to learn some geometry as you're going through these parts too. The first one was the double wedge theorem that was proposed by Gilbert and Poyak. And they said, if we can have two lines, and those two lines have 120 degrees between them, I'm showing you the top and bottom is the 120, and we can make sure that all the points for the set are in R1 and R2 combined, then we can break it up into those two problems. Solve this problem on R1, solve the problem on R2, and then we figure out if there was a point at X, then we use that on both sides. If there wasn't a point, we find the closest one and we connect it with an edge. And so that's a nice way to break it down. So that's a decomposition of the problem. The next decomposition was what was called the Steiner Hull. And this one was proposed by Cockayne. He said, start with that convex hull that we talked about a little bit earlier, and we're going to start chopping stuff out. And so basically using what we just talked about, if we have a line, in this case, if you remember the original convex hull, there was a line along this edge here. Professor, can you see the red dot on the screen well?
Yes.
Good. I forgot to check on that. I'm sorry. Sometimes Zoom behaves nicely and sometimes it doesn't. I wasn't sure. Make sure you're getting it.
Like
so, good. On the convex hull, we originally had the line here, and he said, we want to find the points P, Q, and R such that P and R are adjacent on the hull. That would be these two. And there's somebody else here so that we can have this angle greater than or equal to 120 degrees. And there's no other points in that triangle. Then we can remove the edge and have these two edges here. So that allows us to chop the space that we're looking in down. And depending on the layout, we can end up with some weird situations where we end up with possibly the Steiner hull touching each other, and that allows another decomposition. But this group allows us to throw things out in the computing stuff later. So that was a major piece proposed by Cockayne as he was working on his work. All right, let's go back to code. I don't know about you, I like to be able to write some code to be able to do stuff and be able to see the solutions. So we already talked about Cockayne and Schiller, and they had a 7-point problem that they could code they could do. And then in 1972, Boyce and Siri, I think I'm pronouncing his name right. I've never met him, so I don't know. They were working at AT&T Bell Labs, and they came up with a code that could solve a 10-point problem. And in 1973, they got to 12 points. And this is pretty dramatic because think of an exponential problem. This is growing rapidly in how long it takes to solve. The next key piece was 1981. Pawel Winter, part of his dissertation was a code to do geometry and the code to do Steiner. And he came with a project he called GeoSteiner. And he could do anything with 15 vertices in 30 seconds. And the world was shocked. And he said, and in one of his articles later, he said, well, I think I can do 30 vertices in an hour. And everybody was going, what? Because this code here was running for hours back here. And he has chopped it dramatically by using geometry to optimize his code and what he was computing. So I want to talk about Steiner's, this Winter sequential algorithm. And his whole goal was to build two lists. He wants to build T-list and he wants to build Q-list. T-list is what we're going to take the solution out of. But first, we got to give a definition. So we have what are called full Steiner trees. A full Steiner tree is a tree with n vertices and n minus 2 Steiner points. So if we think of the triangle, we had the 3 points and we put a Steiner point in the middle. So we had 3 vertices, 1 Steiner point. That fits a full Steiner tree. If we go to the 4 vertices on a rectangle, we have 4 vertices and they can come into 2 Steiner points, which are then connected. So we have 4 vertices, 2 Steiner points. That's a full Steiner tree. So our goal is to build full Steiner trees, and those are candidates for inclusion in the final answer. So T-list is what we're going to put the possible candidates into. We're going to prime it with the edges of the minimum spanning tree because sometimes the spanning tree is all that's there. Winter created what's called a Q-list, and it's partial trees. He primed it with the vertices and he said, can we combine these things? Can we combine any of these vertices and then take these edges and figure out, can we combine them to create full Steiner trees as we go along? And he combined them over and over again, but he had some geometry to eliminate a bunch of them. And so he created this Q-list, and from the Q-list, he also put stuff into T-list. And then when he was all done, he said, the answer is in T-list. Let's go find it. And so they searched for it. Now, the first step was to take his paper with the algorithms in it and understand it. And if you look at algorithms that are published in papers, you find out that they're not always as clear as you wish. So that's always my challenge to my students when they're going to write a paper, to make sure the algorithms are understandable, because somebody else may have to implement them. Then I went through and I said, uh-oh, we have a bunch of go-tos, and a go-to, and then we have a go-to. I don't know about you, but it's really hard to optimize code with a bunch of go-tos. And when they teach you stuff in freshman and sophomore level, your first 2 years of college coding, they say, don't use those. And when you're writing, I teach compiler construction also. When you're doing optimization on the code, go-tos eliminate all sorts of optimization. So you can't do the code optimization you want. And when you're doing parallelization and you want to make the code run faster on multiple machines, go-tos even make it worse. So I had to take that code and figure out how to rewrite it without the go-tos. So I spent a bunch of time understanding it and rewrote the code. I eliminated the go-tos, and you've got this loop. Now, I'm going to come to the next page because I'm going to blow this up a little bit so you can see it bigger. In line 1, we have this loop for P equals 0,
in 5 minutes.
P less than Q, P plus plus. So we go from, P goes from 0 to Q, but then we come down here to line 30. And we have a gotcha here. We are changing the loop bounds on the fly. That messes with a lot of optimizations too. However, it makes it very interesting for parallelization and how to do it. And we finally figured out some different ways. So what we had to do is we had to spend a lot of time taking this code and saying, what is going on? How does it work? And what is this really trying to do? Now, what's buried in here is that we have a bunch of pieces of code that are function calls that take a lot of time. So it's not going to be a fast piece of code, but I spent some time understanding it. And we said, we have to take 2 of these trees from Q-list. We'll call it a left subtree and a right subtree. And we have to figure out which one the left subtree can mate with or be merged with. And it can merge with any tree that's shorter than it, if we think of the height of the tree. And it can merge with or mate with all the equals that are after it on the Q-list. But it can never merge with a taller tree. if it's the left one that's chosen. So, wow. Now that we understood it, we could figure out how to rewrite code a little bit to make it run in parallel. So we spent time understanding that part of it. And we did our first attempt. And we used workers and a bookkeeper. So we had a piece of code that was doing all the bookkeeping. Sometimes in the literature, this is called the master-slave model. But with the bookkeepers start a worker for each member of queue list. And then we send it all the current entries on the queue list and we say, go figure out who you're going to merge with and send me back the answers. So each worker starts with his member and attempts to do the mating. And that mating creates new members of queue list, which we send back to the bookkeeper. And if it's an FST, the bookkeeper may also add it to the T list. And when the worker runs out of work, he says, please give me more work, and asks the bookkeeper for more work and continues. And that was fine. We could do up to 15 and 20 people really fast. But the problem came down to, we wanted to do 100 vertices. And when we got 100 vertices, queue list exceeds 1,000 entries. Easily. If we're going to start a process on a different CPU for each member of queue list, this can blow up really fast. Because at this time, it's not a well-balanced problem, so you typically are going to run it on a bunch of workstations as opposed to on a big, large parallel machine, because you're going to find each node is independently working and not working in a nice lockstep. So this was a lot of processes and a lot of messages to work with, and we saw things really bogging down. So we changed it a little bit. And whenever you're working on problems, you have a tendency to read other literature. And we found this paper by Quinn and Dale. And they were writing the paper for branch and bound algorithms. And in the branch and bound algorithms, they said, we can have this work list, but we think you should sort it. And you start with a fixed number of workers, and they request work, and you go through that work list in the sorted order. So we had to figure out how in the world are we going to sort our work list. And so we started doing it on a few different ways, and we ended up with one which was based on the order in which it was constructed. So that way we knew where it fit in the construction list, and it worked really, really well. I think I have some numbers a little bit. So once we had done all that, we created what was called Tlist. And that's the one that has the candidates. And you now have to go through all these candidates and extract them. And you remember Tlist was also primed with with the spanning tree. So we've got edges and we got some partial full Steiner trees on pieces, and we got to figure out which ones do it. And it has some constraints as you're doing this extraction. And they're pretty obvious, but I put them down here anyway because it helps us all remember the pieces. We have to cover all the original points because this had better be a tree. And it can't contain a cycle. And I'm going to show you some preliminary results where we had cycles. And it can't be too long because we know the minimum spanning tree is the maximum length. So it better be shorter than that. So if it ever gets longer than that, we're done. And so we basically are going to go through, and sequentially, you're going to do this recursively with a branch and bound by adding and deleting trees and going through and solving that problem. So what we have here on the left are all the Tlist entries drawn in the plane. They overlap each other. And you'll notice that some are just the original vertices. We have the spanning tree here. And as we go through it, we're going to say, oh, and notice we have a cycle here. We don't want a cycle in the final solution. So as we go through it and start extracting, we end up with what's the final solution, which is the exact one. Now, it's a little harder to see on this type of slide, but the original vertices are the circles. And the Steiner points that were added are the black dots. So for example, where my red cursor is, there's a black dot right above it. That's a Steiner point that was added, whereas this was one of the original vertices. And so you can see it's an open circle. So we have a bunch of Steiner points that are added throughout the graph, and they were extracted out of these trees. And that's typically done in a branch and bound fashion as we're going through it, where we can use the constraints to delete and throw things away. So that we know that back here, we can get rid of the original edge, and we can use the Steiner point that was used here to come across. So that makes things a little interesting to find. So we went through, and we were in discussion with Professor Cockayne, University of Victoria, and he had the full data sets for his 100-point problems. And he was kind and gracious and allowed us to have a copy of those 100-point problems so we could actually compare them. We ended up computing them in about 939 seconds, and he was doing them a little over 13,000 seconds to compute each one. So we were coming up with some really nice results. And we ended up being able to do that really well. We then took that problem and then said, we want to attack some larger ones, and we want to attack grids. And people are saying, why do you want to do grids? Well, this is some of the preliminary work for circuit layouts too. Because if we're going to do circuit layout, we got to understand how they're going to be laid out in grid fashions. How can we have our electrical conduits or the wires between things done really well? And we've done some preliminary work in crossing numbers, which are dealt with also for circuit layout. And we showed that the bottleneck had now moved. When Pawel Winter came up with his algorithm, he had two pieces to it: the creation of Tlist and then the extraction of the answer. And we shifted, basically saying, when Winter did it, the creation of Tlist took the biggest amount of time. And we wiped that out. And we said, we're now dealing with the extraction process. And so that shifted the whole work at that stage to the problem. Now, one of my master's students in 2015 did an MPI version of our code and then set up some CUDA version for the extraction process. Now, we had some mixed results, and the mixed results weren't because of his algorithm. We were on the bleeding edge of technology and doing things possibly a little earlier than we really should have been. We had a limited amount of memory on GPU cards 5 years ago, and the memory bandwidth, which has since doubled for PCI Express 3 and is doubling again this year with PCI Express 4, was a constraint. We couldn't move the data fast enough from the CPU to the GPU. So now with that doubling and doubling again for the memory bandwidth and the bigger memory on the cards, we're about ready to go back and start looking at the problem on GPU computation to do the extraction. And that will be an interesting piece to see. All right, I have a few more pieces here to talk about where we were with grids. So basically a grid is going to be any regular layout of vertices. The first proof for anything besides the 2x2 grid, figure C right here is your 2x2 grid, where you have the, we mentioned earlier, the 4 vertices, and we have the 2 Steiner points in the middle that are connected. So the first proof came on a paper by Chung and Graham, where they proved the optimality on a 2x_m grid. They also argued for 2x2, 3x3, and 4x4, and then they gave some conjectures to go on up. And we were able to go back and replicate their work and then start showing the computation of things. And we came up with building blocks. And now I mentioned earlier that I teach compiler construction. And when you're going to deal with languages, you end up with what are called rewrite rules, where you start with a string and you have something in it that you can replace. And typically in grammars, you have what you call terminals and non-terminals. And you take the non-terminals and rewrite them. For example, a non-terminal may be for loop. And we say for loop, well, that's for, open parentheses, part A, semicolon, part B, semicolon, part C, close parentheses, and the loop body, right? And that's what we would code it in C. So we have these strings that we're going to talk about. So we have parts A, B, C, and D as our building blocks for our 2x_m grids. And we go through it and we say, for a 2x4 grid, This is what our Steiner minimal tree looks like. For a 3x3 grid, it looks like this over here. And for a 3x5 grid, it looks like that. And you're going, well, those look pretty simple to do. Well, it gets interesting when you start shifting a little bit more because you can go to 4x_m, 5x_m, and all the way up. And here's what the 8x8 looks like, because it's really simple. It's a bunch of Steiners hooked together in the 4x4 patterns, and it really gives you an interesting structure of that tree. But I want to go back to the 4x_m's as an example, and that's where I'm going to stop with regards to the grids. We basically end up with what are called 5 of the basic patterns. And we had a 4x, and this case went so far. In this case, it was 4x3. This one is a 4x2, and this one is a 4x3. And we said, we're going to call this pattern A, pattern B, pattern C, pattern D, and pattern E. And so we create these patterns, and we started showing what the strings looked like. And if we have a B, which in this case is this one, we can go from a B and replace it with a C. That's how we can go from a 4x2, in this case, something with this set here, and we can add an extra dot onto it to go to the by3, as we can make our tree longer. And we're assuming that it's hooked up together up here in some fashion. If we have a C, which is this one, we take it apart and put a B, a D to hook them together in the middle, and then another B at the bottom. And so we start seeing these rewrite rules to say, okay, we have in a 4x5, we have an A and a C. We start with this, and then we extend it down. So they're hooked together in this middle part. We follow the rewrite rules. We take the C off, and we put a B, D, B, and we end up with A, B, D, B. And we can start drawing these things by bolting them together. And we end up with a nice grammar that builds and allows us to show how what this whole tree will look like in a nice fashion. And we were able to do this for 4x_m grids, 5x_m grids, 6x_m grids, and 7x_m grids. And we have some of that work that's published in one of the chapters, which I have a link to off of my website. But I don't want to spend all the time here, but I just want to show you that all these pieces that come from different parts of computer science impact the computation. So we have the grammar, we have some of the basic graphics that we get to do, and we get to understand how the compiler would rewrite just like they would for a compiler to take the grammar and rewrite things. You can do this to build up your 4x_m grids. All right, I'm going to stop with that point there. I think I've covered my 30 minutes and a little bit more. And we'll see if we have any questions or not. Thank you very much.
Thank you very much, Fred, for this nice presentation. You covered it all, actually, 45 minutes. Okay, I'm
sorry, I guess well, we did start earlier. Oh,
that's okay. What I liked about your presentation is this passion and love for what you are doing, and which we were able to sense through what you've been doing. So it was nice to follow the presentation from the beginning to its end.
I see that all proposed algorithms are sequential, especially yours. I'm asking if there are some distributed algorithms to compute MST, SMT, Steiner Minimal Tree.
If we go back to, I didn't give all the code pieces. I'm going to back up here. We were actually able to use the work list and the bookkeeper to do this in a distributed fashion. And we were able to get some really good results. That's how we were able to get much better time. I used the sequential piece as the springboard. And then I said I had to understand this whole section here on not the bookkeeper. It has to select a tree and do the mating. And we were able to pull that whole section out. And so basically, if I back up to here, we left the outer loop, and then we pulled a bunch of the inner loop out of it to do the distributed computing pieces of it.
What's happened if the algorithm gives, if we have two solutions, more than one solution? Maybe sometime we have the MST is not unique. We have a lot. There is a lot of solutions.
Yes.
They give the same performance. What's happened?
That's this whole piece on the extraction when we start with this left side here, which is the set. And you're saying, what if this tree is not unique and there's another one that's just like it with the same length? The extraction process is going to find the first one just the same way that the minimum spanning tree would do. So it'll find the first one of that length. And if there's a second one of that length, it will just stick with the first one probably. We could use the first one or the last. We did not do it. We just wanted the first one to find the best one. But we couldn't find a reason why to keep all of them at the same length because we never had because they were doing floating point numbers. We never ended up with one that was exactly the same length when we did the computation. But we could do it that way. That's part of the extraction then.
Which law you use to select nodes?
I'm sorry, say that again?
Which law, probabilistic law? Do you use a probabilistic law to select nodes to belong to this tree?
Because the fact that we have this list, the T-list that was created by Winter's algorithm, we're just walking through them in an order to pull them out, to extract them. Similar to the way you would have the complete spanning tree list. You'd have a list of all the edges possibly to pull out. So there wasn't a probabilistic side of that one.
Okay.
I think I was understanding your problem, but I'm not sure.
Yeah. What happened if the node can move?
Oh, you're thinking of moving wireless networks.
Yeah.
I've never thought of that problem. I like that problem. That would make it an intriguing one because you would have some fixed vertices and moving vertices. I'm not sure how the Steiner points would assist on that part though. That would do if you had drones that could shift to minimize the network length and therefore latency. You could have drones that were doing some of the communication backhaul. Wow, you're making me think of that. I like that idea. I'll have to go look some of that.
It's enough for me. Thank you. Thank you. I give the floor to you, Hazaf. Thank you.
Yeah, thank you very much. Well, my questions are much easier.
Hajar?
Yeah. Yes.
I am Abdel Karim. I have a question, but for example, if the problem is very hard to solve, is it possible to use, for example, a meta-heuristic, sub-meta-heuristic approach in order to have the minimal tree?
Meta-heuristic approach, an approximation algorithm.
Yeah, exactly.
Which is what we attacked first. Let me find. When we did our simulated annealing, that was a heuristic algorithm. And this tells us how close we got to the exact solution because we had the exact solution and we had the spanning tree. And then we did stuff and we never got to the exact algorithm, exact answer on this one because we were doing it with too many points. And when you start going past 30 or 40 points, your capability of getting the exact one with a heuristic starts dropping. And we found that when they were packed, it was even harder if you had clusters that were too dense. But this was just, we were one of the first ones who proposed the percent covered heuristic as far as way to measure heuristics to see how well they were. But yes, that is possible, but I don't know if you can get to the exact solution.
Just two questions just for me. On which criteria you sort the workers? Based on which criteria?
We ended up doing it based upon the order that they were placed into queue list. So as let me see if I can get back to that piece of code. Where's the add to queue? Sorry, my brain is not catching. Oh, this line here. That was to add it to Tlist. Where's the QList entry? Left, right, Q star. I think this one also added it to QList and buried it together. I have to go back and check. I may have missed it somewhere else. Oh, the construct did that. So we added it to QList and then we did the dash, we checked the construction, but it was the order in which it was constructed. And we actually knew that, and when we went to distributed, that made it a little rougher because things were constructed out of order, but we knew who your parent was. So we did it based upon your genealogy, if you want to think of it that way. So that helped us track down those pieces.
Okay. My last question is about writing rules. I mean, do you extract automatically or you have code for it? How do you do it?
That was not automatic. I had to have the insight to see what it was building. So that was basically going to my grammars and compilers and languages are a fun thing for me on the side. That's not where my research is, but I took many courses in graduate school in compilers and compiler construction, optimization typically. So that was kind of a side love of mine, if you want to think of it that way, from the field of study. So it was more, I was seeing the patterns and saying, this looks like it is regular. Can I come up with something? And once I figured it out for 4 by M, it was really easy to track down 5, 6, and 7 because you started knowing what to look for. Now, their patterns were a little bigger. And let's see, I have a chapter. Should I post a link to that somewhere?
Maybe in the Q&A.
Let me find publication chapters. I'm going to give you a link to a PDF. Let's see, where is Q&A is over here. So there's the chat. There's a PDF that went to the webinar chat. Is that where that goes?
Yes.
Which has a lot more of the stuff that I had to shrink down.
Okay. There is a last question on the Q&A. It says, I'm too interested in proving the correctness of the algorithm, and how do you prove it if before the implementation stage, I mean the derivation of your loop-based algorithm?
A lot of the proof, if you go back to the original proofs, was geometric. So Winter had to go through and do a geometric proof in his dissertation. So did Cockayne and a few others in some of their pieces. And a lot of it was geometric proofs. And then they coded the geometry. So that's how they ended up keeping and showing things that were accurate. Shifting to the distributed one, because I did change a lot. That's where it was very nice to have the 100-point problems that Professor Cockayne had done sequentially to be able to compare them against. Okay. And I had my sequential code and my distributed code, so I was able to take both of them and use those two against Professor Cockayne's results. He didn't want to give me his code, and that's fine. But he actually showed me his answers. I said, that's what I want to know, because if I have your answers, I can tell whether I got the right answers too.
Okay.
And so I use them as test cases, if you want to think of that way.
Okay, thank you very much, Professor Fred. And it was really nice, both presentation and discussion.